This
So yeah, so we
conference
can
will
have
now be recorded.
we can have a Q&A session afterwards then.
Sure.
Okay, yeah, so this is being recorded right now. Hi everybody. We're really happy to have Batu Osmanoglu. I hope that's pronounced that correctly. From NASA Goddard Space Flight Center here with us today. Batu is a research physical scientist at Goddard. He has a background in SAR, synthetic aperture radar. His PhD is in marine geology and geophysics from the University of Miami. So in addition to his research work in this area, he's also the Goddard Disaster Program Center Coordinator, and it's that capacity that he'll be talking to us today about some of the work that the disaster group is doing. And as you can imagine, they've been quite busy this year. So without further ado, I'm going to hand it off to you, Batu.
Thank you, Bill. And yeah, no worries about the name. I go with Batu for a reason, and pretty difficult to pronounce the full name or the last name. So thank you again for inviting me and giving me the opportunity. I wanted to highlight a couple things on the title slide. As you said, I wanted to sort of give a little bit a few examples, I guess, about the disasters activities that we are working on. I was originally thinking about going more into the what the disasters program is, or what's how the group is formed. But after we had a few discussions, I sort of switched to try to provide as much examples as for the cascading hazards as I could. And so you will see, I have a pretty much a set of varying applications from a wide spectrum of things that we have looked at over the years. And of course, that would not be possible without having the work done by many of the collaborators that I have listed. And I'm pretty sure I'm missing a bunch of others, but I sort of, these are the ones that I could think of. And as the slides come along, I'll also try to point out, who has done this study, and if you're interested in reaching out to them, how you could do that. One thing I guess I wanted to say is in terms of the cascading hazards, there's several different kinds of cascading hazards that we could think of, or one could think of. Of course, the immediate kind, maybe that draws the headlines and also brings nature articles out of this, is essentially the rapidly cascading event. So, for example, you have a fire, and that you have a heavy rainfall that triggers a landslide, and that triggers flooding. So that type of interaction is very rapid, and it essentially can do a lot of damage also. So it is one of the major things that we're trying to look at. The other things that the other types of cascading hazards can be considered on a slower time scale, and that I will say sort of it depends on how you look at it. There's some of them, for example, the levee monitoring example that I'll give. It has a long startup time, but once you sort of if you ignore the problem and don't pay attention to it, there could be a catastrophic failure. Similarly, I think one could make the case for the climate change, glacier response and food security case, but also someone can argue that the time scale there might be long enough that that this can be prevented. And I wanted to also talk about the COVID-19 and some of the efforts that are ongoing at the very end, and how I think that could have a cascading impact too. And of course, we'll have time at the end for questions, but feel free to interrupt if I say something that doesn't quite make sense. Also, I was wondering if I should turn my camera on. Does that help or does it distract? I'm happy to do either.
Yeah, either way. I mean, it's up to you.
Well, I tried to turn it on, but I won't spend time on trying to turn it on anymore. So maybe it's better it's off. Okay, so in terms of, let's start with the levees. And this is one of the examples that I could think of that, I have been involved since my earlier days, as a PhD student, looking at SAR interferometry. So these levees can be, several different kinds. It could be earthen levees, as shown here in the picture, and also it could be actually, reinforced infrastructure along a canal. Regardless how they are built, they tend to be built over, they're major undertakings, so they tend to be built quite old, since around the time of Great Depression for some of them. And over the years, these things naturally move. And if that movement happens to be, in vertically going down, meaning subsidence, that could actually create a major risk or major hazard if a hurricane comes along and stresses the system. So the point of this slide, this picture, is that unless you are on top of the crack, as shown with the arrows, and as Kathleen is, looking right at them, it's really easy to miss them when you're just doing a drive-by survey of the levees, and that's how they tend to be surveyed. And they move relatively slow. So in the next slide, you will see some examples of the deformation rate. And so as in the fastest case, you're getting about 90 millimeters per year here in this example, which is along the Louisiana coast. But they tend to some can move even slower, which in the next slide I'll show you a more famous example of that one, which we had studied. So this type of analysis is basically the cascading impact of subsidence that sometimes the scientists monitor and are aware of, but the infrastructure people are unaware of, or due to lack of funds, it gets ignored. And similarly, it's possible that we don't know either, which was the case for the next example. In most of these cases, a failure of a levee basically results in major flooding. And the one example of that was essentially happened during Hurricane Katrina, which caused large flooding in New Orleans. And when actually this was one of the first times that I had looked into this study. And if we look at the levee along this MRGO, or we would refer to it as Mr. Go levee, you can see that they actually have relatively high subsidence rates on the order of 20 millimeters per year. And that was actually the levee that failed, resulting in a lot of flooding in urban areas. So we are constantly monitoring similar areas that are subsiding, and one of the major issues, not on a levee, but still in terms of nuisance, is the relative sea level rise of along the coastal areas. They tend to be, again, relatively small displacements. It could be a few millimeters per year, but given that sea levels are also rising, with the tidal loads, it creates this effect of high tide flooding, HTF events, or sometimes referred to as sunny day flooding events. And our very own Annapolis is unfortunately suffering from that. And some of the studies actually say that it's already starting to take impact. It has the businesses lost about 2% of their revenue because of these sunny day events, and one major cancellation that I can remember was the boat parade this year. So if we move away from this, subsidence realm, which takes a long time to develop, but if you ignore the signs, it can impact you rapidly. There is this, I guess the most famous example of cascading hazards that I can think of, which is this, fires, rainfalls, that results into landslides and flooding. So in 2019, there were essentially, again, fires in California, and an atmospheric river event, which an example of an atmospheric river event is shown on the right-hand side to sort of give the people an idea of what I mean when I say atmospheric river. It's just a very heavy rainfall over a narrow band that essentially accumulates over a certain region, and California is known for these things. Once the fire essentially strips the vegetation, there isn't really much holding the soil back, and that results in landslides. And of course, as the land slides and soils are not able to prevent the rapid release of the waters, there's also flooding that is followed. So this year we're paying a lot of attention to California. So far there hasn't been a atmospheric river, but there has been a lot of area that has been burned. And so right now what we are basically doing is building up our archives for the pre-landslide and flooding data sets. So, here's an example, that image from the UAV SAR. In this image, of course, it's somewhat difficult to see from just this image, but I don't know if you can see my cursor, but these areas sort of that are pinkish, pink to purple areas that are outside the farmlands tend to be actually the burnt area scars that we could use these to sort of map the areas that are potential damaged. And Dalia and Robert are running landslide models to identify high risk areas so that we are ready for for the next rainfall event when that happens. So if you are interested in that, please reach out to Dalia. She is the other disasters coordinator at Goddard. So speaking of the flooding in 2019 event, this atmospheric river caused a lot of flooding in the town of Gurneville. So we were approached by the California Department of Natural Resources and to map the flood height, flood depth. So we do this analysis using both radar and optical data. And this example here that you're seeing is coming from the Planet satellite. I do not know why the reference is not there. But in any case, we use the Planet flood extent and combine that with a well-known DEM that we can essentially estimate what the flood depth must be given the flood area. And we also have a ongoing project for this with Alaska Satellite Facility and Marshall Space Flight Center, looking at the impacts of severe weather events and for agricultural areas. And for that study, our role is essentially to look at how long a given agricultural area stays underwater, and how we could come up with a model to estimate the loss in the agricultural field given the crop cycle. So we're working with USDA Foreign Agricultural Service for that. Another, I think, classic example of rapid cascading event is that something, again, that Dalia has been working a lot on, the rainfall-induced landslides. And in this case, what I'm showing you here is the Jura landslide that took place in 2014 in Nepal. And basically the landslide hit and killed about 156 people in the town of Jura. And it essentially dammed a river, causing further risk of outburst flows over the same town that was essentially just hit by a landslide. So in this case, what you see on the image is the deformation rates, again, from synthetic aperture radar before the landslide. The area of the landslides are shown also this colored image. And you can see the blue dots showing the lake that actually formed because of the damming of the river. So luckily, what they were able to blast part of the blockage and release the water slowly. But nonetheless, these things are very scary, and they happen quite a lot in mountainous terrains like Nepal. So on the longer time scale, but staying to in the same region in high mountain Asia, we looked at how the climate change is impacting glaciers and how that might in the future impact agriculture. So this is just to orient you, but and also it shows the main data sets that we have used. The images that you're seeing are on the top row are essentially the topographic map of high mountain Asia. The second row basically shows the number of repeats that we have given different sensors, whether that's high resolution commercial, such as the Worldview or GeoEye, or the Aster, the medium resolution instrument on the right-hand side. And then at the bottom, you can see that the uncertainty metrics that we can observe. So the point of this slide is that with these two data sets, we were able to get a lot of coverage, and the Worldview data was much higher quality in terms of vertical accuracy, but we were also able to combine the higher repeats with Aster. And finally, using that, what we did is essentially to combine it with our models, and we looked at how the glaciers are losing mass given climate change, and we essentially looked at how each basin is impacted. And we did this both, for individual sampled glaciers, and then also putting it into a glacier model and running it over all the glaciers that are in the region. And finally, what we get from once we know the glacier area loss, glacier volume loss, we can actually track how much water is at stake here. So this is basically another model that allows us to track how the glacier runoff is changing and how it is being used, and also how much of this glacier runoff is actually being used in irrigation. So on the right-hand side, what you're seeing is a historical average from 1980 to 2015, and what you see is that there is quite a lot of that glacier runoff being used in irrigation of agricultural land. So the question was basically, as these glaciers shrink, what happens to the agriculture? And in order to look at that, we sort of looked at this area that is being used for irrigation, and we then basically ran several scenarios. I'm only showing the 8.5 scenario, but in most of these basins that I showed in the previous slide, basically we're reaching a peak water year of at around 2050, which means that glaciers are losing water so much that there is not much glacier left that they can keep up with the loss anymore. And so as they start shrinking, there's less water available. So until 2050, there might actually be more water coming from the glaciers because of the increased temperatures. But once we hit about 2050, we expect that water will start getting less and less available. And then, of course, what that means is that means less recharge available for the storage on land. And if you're familiar with the area, there's already several agricultural areas that are pumping out water so high that they are creating anomalies that can even be seen with Grace, which has a footprint of hundreds of kilometers. So if you're interested in food security work, Stephanie Uz has been leading a group at Goddard, which I was a part of, and we published a small article about what different sensors can do for agriculture and food security. So that would be the point of contact that I would suggest you could reach out to. And again, as I said, we have a severe weather agriculture project, so if that's of interest, let me know. And finally, I guess I wanted to talk a little bit about COVID. And the reason why I think that's sort of becoming a cascading effect is essentially any disaster on its own is a shock to the system. And when that happens, basically we lose the preventative measures that allows us to not get sick. And this is a study that was done before COVID. And so I guess these examples, this figure is actually from a more recent study, but there, you can look at the literature, and there's already many articles about how different types of infections could actually spread more readily when there is a disaster. And of course, there are several examples of that. So, one thing that I can highlight is in the case of an earthquake in Italy, the L'Aquila earthquake, there was essentially an increase in the infectious diseases, such as COVID. In cases of flooding, if you run through the water or are subject to the water, that can, cause bacterial infections, as shown in an earlier study in 2010. But and all of them tend to have a different signature depending on, of course, the disease. But they all start with the disastrous shock. So, for several things that we have been looking at, for example, we looked at the cyclone Amphan this May, and which resulted in a lot of flooding in Asia, and especially in India and Bangladesh. And there are studies now, which is cited at the bottom of the slide, that are suggesting that there might be an increase of COVID-19 due to the cyclone. And there was a similar study done by University of Florida hydrology Gerald and hydrology lab for cholera, and they were essentially looking at the impacts of the flooding and the risk of risk of cholera as a vector disease. So you might ask why this is the case, and the figure on the right is a recent picture from the earthquake that happened 2 weeks ago in Izmir, Turkey. Obviously, there are lots of COVID-19 precautions in place, and you can see some people that are wearing masks, but a lot of the people are actually just trying to help other people, and therefore they are putting their guards down, which is providing an opportunity for the virus to spread. In addition, this earthquake resulted in loss of homes for about 15,000 people, which we are trying to also identify, looking at both the synthetic aperture radar, damage mapping, damage proxy maps, which is shown on the top of the figure in A and B, and also using the high resolution optical imagery, again from world view at the bottom in C and D. And since all these people that have lost homes will be looking at temporary living arrangements, they'll likely be also in close quarters, getting more in touch with other people and resulting in more of a spread. So we are monitoring that situation as well. And NASA is actually leading a COVID-19 task force with many of our nation's agencies. So if you're interested in joining that effort, please let me know. And they are looking at, they're not only looking at disasters, but also looking at how COVID-19 is impacting the environment and the people. So it's a very large spectrum activity. So for example, for that study, we provided an example of how slowing down of ports result in increased numbers of ships waiting outside the ports, clogging the trade, international trade, essentially. So with that, I'll just thank you, and I hope I didn't take too long, but I just wanted to give you some examples of what we're working on. Thank you.
Well, thank you, Batu. That was quite a range of activities, disaster-related activities that your group is covering. Pretty impressive. No wonder it keeps you so busy. So we have some time for Q&A. If anybody has questions, please go ahead.
Hey, Bill, I have a question. Can you hear me? This is Ellie.
Yes.
Yes, I can.
Okay. Hi, Batu. Great presentation. Really, really interesting. I was actually just talking to, so my research is in COVID-19 and the hazards and compound hazards and their impact on small businesses. But I was talking to a friend of mine who works in public health, and she was saying that 2020 had been the goal to eliminate a lot of the larger scale diseases such as TB and polio, and that this has actually set us back basically to where we were at the early 2000s. Is there anything that's being done about that, or I guess how is that being studied?
Yeah, so I actually haven't heard in terms of that particular example, but I imagine people are looking at it because we have a so Stephanie Uz is actually quite interested in health and remote sensing applications regarding health, and also I know that the Applied Sciences program has a specific focus area for health, and which is tied into the COVID effort. So I imagine they're looking at that as well. But I have not heard how COVID-19 impacted our fight with other infectious diseases in this year. But I can definitely try to reach out and maybe put you in touch with the Applied Sciences program that is working on that.
Great, thank you. And I have a follow-up question about kind of the economic side of things.
Sure.
Because that's where my research is in terms of small business impacts. Is there work being done on mapping small business loss? I don't know if looking at parking lot illness or something like that.
Yeah, so it's funny you say that because Arif Albayrak and I have been discussing if we could, collect some information on exactly that, what the impact of small businesses are from social media. But aside from that discussion, I know that headquarters funded a project with Sang Ho Yoon at JPL, looking at the they're using a technique similar to that was done, for example, in the earthquake case, which provides you the damage proxy, and they're essentially modifying that technique to look at the parking lots the airports, the seaports, and how high the containers are being stacked up, and how full they are, and also I think they're even looking at the where the airplanes are parked, since they're not flying, and they're trying to sort of get a sense of how high the what the impact is in terms of I guess people's mobility and also businesses. But of course, you can imagine that for these things to show up in the remote sensing data that we're using for these things, they tend to be on the order of about 10 meters, which means that it has to be like a larger impact, and that's why it is difficult to get a sense of the closed business and or small businesses and how they're impacted. That's sort of why we were thinking about maybe looking at the social media to sort of complement the ongoing efforts that Gerald Bowden at headquarters is pursuing with Sang-Ho Yoon at JPL.
Great. I would be really interested in hearing more about that, since I'm measuring it on a smaller scale through survey data.
Mm-hmm. No, that sounds great. So are your surveys local in the area, or do they cover a larger area?
I'm doing two different ones. One is in the Carolinas, so in South Carolina and North Carolina, and then one of them is a national survey.
Okay.
Of small businesses.
Yeah. Okay. Yeah. No, that sounds great. So yeah, I'll reach out to the the disastrous program to sort of like to get the latest on where Sang-Ho's study is. I guess I can also ask Sang-Ho, and then I'll keep you posted if we actually end up doing something with the with our social media idea.
Great. Fantastic.
Any other questions? Well, I have a short list, so I'm going to just do one of them right now. So, Batu, so you, I think was a second example related to precipitation, or fire precipitation, landslide, and so on. And you mentioned that the in particular Dahlia group is looking at kind of knowing that the fire has occurred, but before the landslide, and therefore that the vegetation is gone, and so some sense of the susceptibility to future landslides, right? So I just wondering, how is that information being used to take action to mitigate this potential damage that that's being forecast?
Yes, yeah, no, that's a great point, and that sort of always comes down to our communication with the decision makers and our end users. We often refer to them as. But one thing that we are very careful about is that NASA does not have an operational mandate, and so we like, for example, we cannot really say that hey, this town is under high threat and we need them to evacuate, for example. I think we can, so NASA's mandate is basically to look at the data and see what it sees and try to disseminate that information. And that's essentially what we are trying to do. For California example, we are again in touch with both the decision makers and people on the ground, including the firefighters, through Maggie Glasgow at JPL. And so she would be the point person, for example, that this information gets sent to, and then she disseminates it to the decision makers and tries to make sure that the information is available for them to make the right call. But in what's usually happens is that as soon as So one of the key important things, for example, for the landslide model is how saturated the soil is. So, so of course, we can run the risk, hazard model now and get an estimate of, areas that are under risk, but that would only be valid for the current soil moisture conditions. So the longer it takes, from between a rainfall to the next, atmospheric river event, it's actually the hazard goes down as the soil sort of dries and it increases its capacity to hold water. So basically, as this atmospheric river forms, we are in a race to assemble the soil moisture data at the highest resolution that we have. So we already have the digital elevation models, and then we are able to sort of run the model again with that at that moment soil moisture data to get a accurate read. And of course, there no model is perfect, and for disastrous program, I think we aim at a 80% accuracy. These are not the typical scientific papers that we would publish with like 99% accurate models, but at least it sort of gives people a list of areas to prioritize in terms of risk and what they should pay attention to.
Thanks. So I guess related to that, you also mentioned about the short-term, long-term timescale in terms of the cascading, right? So it seems like what you just mentioned is like the relationship between the long timescale cascading and the short timescale cascading. Those are not very directly connected.
That is correct, yeah. And the issue with the long time scale cascading impacts is that, we are humans, we all have a short-term memory, and we tend to forget. So that was essentially what had happened in New Orleans, for the levees. Like everybody knew that there was subsidence in New Orleans. Everybody knew that those levees were put in place a long time ago, and everybody expected those levees to be moving. But what we didn't do a good job of is essentially keeping track of what that is, and also just measuring the subsidence, for example, doesn't really get you anywhere unless you couple that with a hazard model that says, okay, if I get either a hurricane or due to a hurricane or due to a tidal load, that I have this height of water against this levee. What is the chance of that levee giving in? And so essentially for New Orleans, I think we had failed to do that in advance. So for example, that example that I was showing you was done using prior to hurricane data, but after the hurricane. So all we could do essentially when the hurricane hit was to simply look at the flood extent and try to estimate the flood depth in a much simpler way than we are doing it now, but in a sense in the same way, and essentially get that information to the South Command, who was down trying to help people, stranded people out of their homes. In a way, I guess what I'm trying to say is that the short-term cascading events are luckier because our attention is on them.
Mm-hmm. Right. Great, thanks. Other questions?
I bored everyone to death. That's perfect.
It's not going to go down my list. So I have a more general question.
Sure.
So, in fact, in next month, we will have a speaker from Amir Ag&Climate from UC Irvine. We're talking about compound disasters, and he has done some work and published, with that terminology, anyways. And and to me, in my mind, cascading and compound disasters are related, of course, but not exactly the same. I was wondering, do you make that differentiation between the two?
Yeah, sure. So, you know, for the disasters program, sometimes we go through planning activities, sort of, you know, where we have a scenario and we essentially go through the moves of how we would respond to such a disaster if that was real. So in one of the you know, more recent cases, we were, for example, working on a made-up town of Disastro, and their Disastro was very unlucky. You know, there was a volcano erupting, which at the same time a hurricane was approaching Disastro's shores. So of course, you know, the idea is to stress the system in terms of how we would, you know, change the ways that we are, you know, trying to guide the end users, decision makers about, for example, okay, you know, if there was only the volcano case, this is where you can safely, you know, relocate the people and, you know, establish a base for housing, shelter, or water distribution. But now, if you also have a hurricane coming in at the same time, which would be a compound disaster, then you have to say that, okay, like in lower lying areas, we will likely have issues due to rainfall, and the ash will turn into, you know, sludge and fall down. So you know, we also have to consider those things. And so those are not necessarily related events, but they are basically happening in such close you know, proximity in time that you have to basically treat them as a single disaster, hence the compound disaster. But the cascading disaster, on the other hand, the way I see it at least, is more that, you know, one disaster sort of prepares the scene for the next disaster, and without the first one, you wouldn't have the second one. So, for example, you know, if with no fires, we would maybe have the atmospheric river event again, but the resulting landslide and flooding would be much smaller without the fire.
So in the cascading case, there is kind of a causation links, whereas in the compound case, if there are these kind of links, they're much I guess much weaker or much more tenuous to causation links.
Yeah, I guess it's independent of the causation, I would say, probably. So, you know, I guess it's, you know, if you were to, you know, consider a large fire, and then there's also a large rainfall event at the same time, you know, maybe one would say that, well, that could be also compound. But I guess the key there is that it's I guess, you know, compound has more of the timing, while cascading has more of the succession of the disaster. Yeah. So I think, you know, we are paying a lot of attention to cascading hazards, mainly because we do not want to fall into a situation where we are, say, looking at the fires so much that we forget about what comes next. And you know, and it's very easy to do that, especially, you know, with our scientific mindsets, that you know, we can work on a single problem for a very long time, but, you know, we have to keep an eye on the next potential threat, and how the current changes on the ground impact that.
Yes, in the case of fire, so like not the immediate response, but also not a very, you know, long-term recovery response, but more like from the days to the weeks kind of response to mitigate any subsequent or consequent disasters.
Yes, that is correct.
I think it's really interesting hearing that the like different definitions, just because So I'm in the University of South Carolina's Department of Geography, and one of our professors wrote a paper about this like semantic difference between compound and cascading and complex. And I think, Bill, you're right that there is a lot of confusion about what the different terms mean, and I think actually we define them slightly differently. So it's really interesting to hear that to your definitions.
Yeah, I'm actually not surprised. I as part of one of my other hats, other jobs at Goddard, we run workshops with the applied sciences community for the future SAR mission, NISAR. And one of my favorite moments in those workshops was that when we asked a bunch of a room full of wetland scientists from various agencies and universities and industry what their definition of wetland is, and there were maybe 10 different definitions, and the room essentially could not agree what how you would define a wetland. And I'm it's unfortunate, but I'm not surprised to hear that the definitions of compound and cascading are different too.
Yeah,
and let me just comment that there are different kinds of phenomena being cascaded. I mean, if one type of hazard affects the probability of another hazard, or the exposure to the hazard, or the vulnerability to the next hazard, those are different processes. You could have a hazard that moves, that as a result of the hazard, people move into an area that's more hazardous, less hazardous. You could have a situation where, I think as you talked about, the state of the soil moisture affects the probability that the next hazard or extreme event will lead to problems. But you can also have, stresses not just on levees, but on nuclear power plants or transportation systems or whatever that lead to cascades in different parts of the disaster life cycle.
Yes, no, that is very true. You're right.
Ellie, you mentioned complex also, in addition to compound and cascading. So how do you define that?
What was that, Bill?
So we were talking about compound and cascading, but you also mentioned complex disasters.
Yeah, I think complex at this point, or at least how we're using it, is as more of an umbrella term because people haven't been able to figure out what they mean by compounding and cascading. And I've been reading a number of people starting to use complex just to mean like there are a bunch of hazards all happening at roughly the same time, roughly the same place, and it just makes things complex. And not trying to go into that semantic difference of what does compound or what does cascade mean, and the danger of implying that there's a domino effect of any of these. And what does that mean? So I've started to see complex pop up more often.
Thanks.
Yet another semantic terminology to add to the pool.
Right. Any other questions? We have just a few minutes left. Okay, I got one more quick one, I think. So I think you mentioned you use at least one example. You use the planet data or planet images. Yeah. So how closely is the Goddard disaster group working with planet? Like what's the relation between the two groups?
Yeah, so we are actually trying to use it as much as we can. So, for example, for the Izmir earthquake, we also looked into the planet data, but the resolution of the imagery was not actually enough to tell us what's going on the ground. But I guess what we notice is that I know Dalia is using that a lot in terms of assessing landslides, and more, I guess, the scars of the landslides after they took place. And we are using it mainly for urban flooding, which is difficult to do with using radar data. So whenever there is urban flooding, if the clouds are not an issue, we try to lean on the planets or other optical data. Couple things also we tried are looking at sort of the oil spills, with the Russian oil spill. But in those cases, essentially, Planet already generated the results before our team could. So, because Planet also has a disasters team, which our disasters program has a good working relationship with. I think one thing that I can say is that the disaster, the Planet data is available to NASA scientists through the agreements that they have, and the priority or the access, the default access to that license is for data that's at least 30 days or older. So for disasters type events, a couple of the coordinators at headquarters, they have access to Planet's daily data, daily imagery, and that's what we use for looking into disasters. But for scientific studies, you could also use it, and the caveat there is that it only goes up to the 30 days prior to current day.
Mm-hmm. Great, thanks.
Yeah. And I guess speaking about commercial data, there was a call recently for which included also the Planet data related projects, and I heard that there might be another call coming up for SAR, synthetic aperture radar related commercial data by later parts of this year, which there's not many months left in this year. So but I don't know exactly when that will come out, or even if it will come out before the end of the calendar year.
So this would be like via some kind of proposal process?
Yeah, I think that will be through the ROSIS proposals. Yeah.
Okay, great. Any other questions? We've got 2 minutes left.
I have one more question. When your team is working on these compounding or cascading disasters, what is the time frame that you're looking at, like relating to each other? Because like the river might have what is the general time frame?
No, yeah, that's a very good point, and we don't have a formula, unfortunately, but it's not because of lack of trying. We do try to come up with a objective way to look at these things. But for example, for California, we know that there's a large area that's burned, and those areas haven't slid yet. So we expect that they're going to slide. So then the question is, when is that going to happen? And essentially what we're telling ourselves by preparing for the atmospheric river is that, hey, we have to keep an eye on the next big rain event. So of course, we might not get an atmospheric river event, and then, but just, it might just rain as normal rain, and then eventually then then probably in spring, all of a sudden we would start having with increased snowmelt and increased rain, we would have landslides. So I'm not sure if you would call it a cascading event still, but for now, at least, we are keeping that open. Yeah, I do not know the answer to that question, to be honest, but it is something that we have been trying to figure out, like how long do we keep an event open, but usually, what we are lucky with is that most people that are working on the disasters program for looking at these events are also scientists, and they have scientific interests, which span a lot longer time frames. So even if the disasters program ends the activation, it's usually there are still people that are looking at it day in, day out, and maybe at a less intensive way, but still paying attention.
Great, really interesting. It's definitely a question that I keep asking myself as well. So.
Yeah, well, if you do find the answer, I'm very curious to know. So let us know.
Okay, so we are at the top of the hour. Any last quick questions before we wrap up? If not, so Batu, thank you very much. It was a very, very interesting talk, giving everybody a look into the Goddard Disasters Program. And before we go, I just want to, one last commercial. So we're making planet data. So in 2 weeks from today, in our second meeting of this month, on the 24th of November, Thomas Harris and his colleagues at Planet will present on the use of some of the data for post-wildfire monitoring and analysis. So that's coming up in a couple of weeks, so we'll have information on that to everybody. So thank you very much, everybody, and thanks again, Batu. We'll talk soon.
Thank you, Phil. Thanks, Ellie. Bye, all.
Thank you.
Thank you, everyone. Bye.
Bye.